So there's 4 voltage amplifier types. We just looked at the voltage amplifier. Here we have a voltage input and an ideal voltage source on the output, and a Thevenin configuration, which outputs the input voltage seen across the input resistance. It amplifies it by a scale, A V naught VI times VI, and that comes to the output as a voltage V out, and we have R out, output resistance. So that's a voltage amplifier. And if we transform this output from a Thevenin we transform it to a Norton output, keeping the input the same, then we would have a current source, an ideal current source on the output. And now we would have this R naught resistance would be in parallel with the output source. We could still see that we still have VI and RI. And now we have some factor, a transconductance, which multiplies the input voltage to produce a current. So a transconductance has units of amps per volt. And we could still see an output voltage, of course, and we have an output current up here. We have an output current coming out here. We still have those, but this voltage source, GM VI, for that value of current, or that current source, GM VI, is doing the amplification now. And we would call this a transconductance amplifier. And of course, now we have a Thevenin or a Norton output. So GM, what is that? It's a transconductance, units of amp per volt. So when we multiply the VI, the volts, we get an output of current, right? So GM times VI would be an amp per volt times a volt, which equals an amp. Ideally, RI here equals an open circuit, just as it is here. But here, in the case of a Norton, ideally, we have an open circuit on the R naught, R out, whereas on the voltage amplifier, ideally, we have a short circuit. We would like to lose no current or no voltage through that source or through that resistance in the case of the voltage amplifier, but in the case of the current, the Norton source, we don't want to lose any current coming down here, and so we would have a infinite output resistance ideally. So it's a transconductance amplifier, and we define GM. I'm not sure I should say define, but it's I out over VI, or V out is equal to 0. that means we're talking about, that's a short, right? Short the output, which means that we just put a wire between there, and we see how that no matter what the value of R naught is, the current will all flow through a short that you attach there. So then that's the you can see that the GM must be by this, because the output current is the same as man, I wish I could point on this. I have to either use presentation view or this view, and I've got a better set of pencils in this view. This current here, if we short the output, if we short the output with a wire across here, then I out will entirely go there. So that's how we get this definition. In that case, well, that's just how we get that definition. So you might say, what use is this kind of amplifier? How do you do that? Well, in fact, a transconductance amplifier is what a transistor is. So a MOSFET transistor is a transconductance amplifier in the configuration that we almost always use it. So in that case, we have an input voltage, and a MOSFET natively really makes current. It produces current. We can turn that current into a voltage by running it through a resistor, but transistors are transconductance amplifiers. Virtually all of them are. So BJTs are too. They're not exactly ideal. They don't necessarily have zero output resistance, but they're absolutely a transconductance amplifier. And so this shows up all the time in amplifier circuits, transconductance amplifiers, because we have transistors. And so this would be the model that we had used to represent a transistor. Now, I drew in the input current here. Well, I didn't draw it in there yet. IN. There really is an input current. There's an input voltage and input current. And instead of having an input voltage, we can consider IN to be an input, and then we'd have a current amplifier. So that would look like, we would still have an input resistance, but now we have a current source here, an ideal current source, which amplifies that current. So we have IN flowing through RI. We still really do have a voltage there. We have R out. We're producing output voltage, we out there, but we're also producing an output current. And now we have a amplifier here, which has a AIS IS amplification. So that's a current amplifier. And ideally, the input resistance is equal to 0, and the output resistance is equal to infinite. And AIS is equal to I out over IN. It's a gain, right? Where V out is set to 0, it's shorted. And so this would be the AIS is the output short circuit gain. And if you could reasonably guess, now there's a fourth type where we have an input current and an output voltage. There's a Thevenin on the output. So we have VI here still, RI, and we have a current IS, and we have this resistance I out, and we can see a voltage, of course, if we want. And now we have RM II, making that current. And ideally, II equals 0, and R out is equal to 0, ideally. And Rm is a trans resistance. And that is Rm is equal to the output voltage over the input current. So we transform a current into a voltage when I out is 0. That's an open, right? And this is a short. So it's a trans resistance amplifier. These are, I mean, we always have a input current, and we always have a output current, and we always have an input voltage and an output voltage. You know, we might be setting those to 0 or something in some cases to test things. So they're always there, and we always have an input resistance and an output resistance. So we can easily transform between these different versions of amplifier. They're all equivalent. But the important thing is that one usually works better than the others. So in the case of a transistor, the transconductance amplifier works by far the best to represent a transistor. So we usually use it for a transistor, but we could transform it into one of these others if we wanted. And in fact, a BJT can also be considered as a current amplifier. So a BJT can also look like a current amplifier. And we could, sometimes it makes more sense to use this equivalent circuit for a BJT. It just depends on the situation and what you're doing. And I'm not expecting you to be able to understand how to do those or decide which one to use, but you need to understand when I show you one, when I show you another, you need to understand that it's equivalent to all these others, and it's just we've made a transformation and be able to understand and accept that. So you might be kind of concerned, you know, what is this input resistance and output resistance? Rn, it's not necessarily an actual resistor, but it is VI, the input voltage, over the input current, right? So if in any of these, I always drew in the input voltage and the input current. And if we know those two things, if we could measure those two things, then we could calculate what a input resistance would be. And that input resistance is just sitting there. It's this resistor right there. It may not be a real resistor, right? It may just be something that we understand in effect. If we consider that circuit to be a black box, then we can say, well, it must be, it's like there's a resistance in there because we can measure the input voltage and input current, excuse me. Same thing with R out. It's equal to V out over V in, or I in, I out, in exactly the same way. If we can measure the output voltage and the output current, then we can measure whatever voltage must be or resistance must be there. So it's when I say that, it's like we've got a black box. And if we can measure a voltage, V in, and we can measure a current, I in, and we can measure it coming out also, and we can measure an output voltage, and we have an output current, I out, and we can measure it either way. If we can measure those, then we can calculate. There is, it's as if there is a resistance Ri there and R out there. That's where they're sitting inside this invisible or this black box that we can't see anything in. It's just those are there. They're just existing. And so if I drew that box around one of these amplifiers, if I drew a voltage amplifier, this black box could be the same as that. It can be exactly the same, where we've got a input voltage and an output voltage, an output current, and an input current. If we could measure those quantities, then we know what value of Ri must be in there, and what A naught Vi is in there, and what R naught is there. If we can measure those input and output currents and voltages, we can figure out what we could arbitrarily decide what's inside. It's not actually necessarily what is inside, but in effect, it's as if that's what's inside. and that brings a whole bunch of simplifications and makes things a lot easier to deal with if we can sort of abstract it that way and work with the amplifier that way. Often to measure, to find R out, I should be more careful. To find R out, we can't just measure I out and V out. Let's say to find R out, what we often need to do often what we'll do is apply a test source. And in reality, we could actually do this in some situations. Apply a voltage Vx and or a current, measure the current Ix, and then R out is Vx over Ix. It's usually a circuit kind of thing with the input set to 0. So we apply 0 volts or 0 current to the input, and then when we see what we get looking in there. And in this case, if we applied 0 volts here, if we shorted this, right? So then Vn equals 0, then this would be 0, and a voltage source, which is 0, is just a short circuit. So we'd have a short straight to there, and we would see R out is equal to the R out that's already existing when we apply this Vx and Ix. You don't have to worry about that too much. We'll do that more like in maybe November or something, but I just want to mention that so that you can recognize it so when it comes up. Now, all of these models are assuming they are unilateral. So we're always assuming that these are so by unilateral, we're assuming that that the signals flow from the input side to the output. I better fix that. Oh, come on. So we're flowing from this input side on the left through to the output. We always assume that in this case, at this stage, that they're unilateral. Later on, well, actually, in the next chapter, we'll make an amplifier with feedback, and that's no longer necessarily unilateral, but in fact, we can generalize even that and understand it as to be a unilateral network, two unilateral networks in combination, but we'll go through that. So briefly talk a little bit about frequency response. We'll really spend more time on that in the spring. What if we apply a sinusoid to a linear circuit? The output is also a sinusoid. So the output is a sinusoid. With identical frequency. But amplitude and phase may change. That's what linear circuits do. And there'd be a transfer function. Which is a function of frequency. And it has a magnitude. That's hard to read, isn't it? There's a magnitude of the absolute value of this transfer function. Not the absolute value of the, well, that's how we find the magnitude. It's not absolute value. V out over VI, and it's usually in dV. As in 20 log d omega. And there's also phase. And there's lots of ways to represent that. If we know those two things at a frequency, then we can predict the output due to some input at that frequency. And we usually make a table of that, or a Bode plot representing the frequency, the gain versus frequency. There should be log. And for a general amplifier, it looks like this. And we would define some points. There's a omega, I'm just going to call it 1 right here, and another one. And these are the value, which are 3 dB below this flat area. Call that midband gain. That's fascinating. The same exact thing happened to me at about that same amount of time. Hopefully I'm still recording. Wonder if it deleted the presentation. It just doesn't like talking about frequency gain, I think is all it is. So it's minus 3 dB. We'll call this area midband gain. And these slopes fall off at minus, or at 20 dB per decade of frequency. A decade of frequency is a 10x change in frequency. So from 10 hertz to 100 hertz. And we call this the bandwidth. We hear about bandwidth all the time, and that's what we're talking about. Wonder what happened. Let's stop the share maybe.